And this actually works quite well on most, but not all networks. There are indeed some networks that establish a minimum time to live. And what that means is, yeah, you may say, please only store me for 0 seconds, but it actually stores it for 5 minutes. And these networks are all happy. They're like, oh, we're safe because you can't rebind us because we're going to hold on to this address for 5 whole minutes. Because an attacker can't wait 5 whole minutes for their attack to succeed. They're really impatient that way. Yeah, about that. There's another method, and it's called spatial rebind or spatial modulation. When you look up a name, the name can return multiple addresses at the same time. And those records can have like an infinite TTL. Now the question is, which record is the browser actually going to use? I don't know. It'll use one of them. Okay, well, what if it picks the wrong one? Try again. It turns out you can detect in every context when you made a connection to the wrong IP address. So, if you're using spatial modulation, try, and if you don't get the expected results, fail, kill the flash applet, start a new one. Eventually you'll get it right. This was actually a lot of fun when I was testing this, because it was a total brute force solution. I'm not getting windows that are necessarily reliably opening up to the right address. I know I'll open 10. One of them will. And totally did. And this is actually the technical description of how to do it. I have so much to go over. You can refer to the slides, which are not on your CDs or in your books. They'll be on the website. Then there's the fun one. This comes from actually knowing how DNS works. People are trying to use DNS TTLs as a security technology. Guys, they're not a security technology. In fact, finally, we have something even less a security technology than virtual machines. If you'll excuse the annoyance, Tommy the Tank Engine security is not good. I think it's safe. I think it's safe. No. TTE. It turns out that overwriting a TTL, if you actually control the legitimate record, is very, very easy. In fact, it's supposed to be easy. It's by design. When something wasn't designed to be a security technology, please don't be surprised when it doesn't actually act as one. So here's what you do. I call it CNIPing, right? It turns out in DNS, when you look up a name, you can get an address back, or you can get something back called a CNAME record. A CNAME record is, yeah, I know you talked to me, but who you really meant to talk to was this name over here. And here's its real address. When you get a referral to a different name, that name can contain, and actually is supposed to contain, the genuine address of that alternate name. That genuine address that comes in the CNAME overrides whatever's in the TTL. It doesn't matter if that thing could have lasted for a year. It's like, oh, okay, well, I got a new name. Got it over there. Came in, it's fresher, it's newer, it's updated. So, to actually look at this in action, we're going to look up 1.foo.mallory.com. 1.foo.mallory.com has been CNAMed over to bar, and bar has an address of 10.0.0.0. And we look it up, and yeah, when you look up bar, it's 10.0.0.0. Now we're going to look up 2.foo.mallory.com. And 2.foo.mallory.com, same CNAME, but now it's going to 10.0.0.1. Take a look. What's the address for bar.foo.mallory.com? 10.0.0.1. Doesn't matter that the TTL didn't expire, guys. The CNAME overrode it. So, to review, by swapping addresses out from underneath a web browser, we can get arbitrary TCP and sometimes UDP access to hosts reachable by the client. Now, what can we do with this? Well, I've been doing tunneling for a long time. Can we VPN completely into corporate networks using nothing but a compromised web browser? Excuse me, a lured web browser. No code execution required. Sure, totally easy. Okay, I'm kidding. It's a bit of a pain in the ass. It took 7 programming languages and 6 protocols, but totally easy. I'm serious. What is up with web programming? Every time you cough, you're in a different language. It's not like a new language. It's like a variant. It's like a smooth continuum of programming. So, how are we going to do it? Well, we have 3 actors in our little dance. We got a browser that has access to the nice and gooey internal resources. We got an attacker that really wants that access. And we got a proxy that wants to bridge the attacker and the proxy, the attacker and the browser together. So we're going to start with the proxy running software that I wrote. This software is called Slurpee. And I'll explain why in a bit. Slurpee, the proxy, is a multi-protocol server. It's built using the Perl PO environment, the Perl object environment. Very, very nice for actually building systems like this. It speaks a couple protocols. One protocol it speaks is called, it accepts TCP streams for a browser to deliver. Each of those TCP streams has to contain some routing data. So, attacker has streams, got to get serviced over at the browser. Slurpee's going to accept that. Slurpee's also going to accept HTTP requests. Browser's coming in, wants its routable traffic. Slurpee's going to provide that over HTTP. Slurpee also provides DNS support. At the web layer, it needs to route. There's all these routing directions that I'm giving it. How are these routing messages actually transmitted? We're using DNS as a routing protocol, which actually, if you think about it, is totally not even an abuse. And actually, finally, XML socket requests. Flash has a thing called XML socket for determining the policy. What ports are allowed to be connected from what servers. It turns out it's a very simple protocol, but by adding support, we get ports lower than 1024. The basic theme, and I'm going to be reiterating this a couple times, is attacker connects the proxy, which manages the appropriate resources in the browser to service the attacker's connection. That's what's going to happen, because the proxy gets to send code to the browser. Not arbitrary code, not executable code, but not nothing. A proxy gets to update the browser to speak the necessary flash to service the bytes being sent by the attacker. So, now we get into the fun terminology. Browser connects. Establishes an iframe called a bucket. A bucket is a collection of connection managers. And the bucket actually polls, and yeah, it's inefficient, I can fix that, but the bucket polls for new connections to establish. The attacker goes ahead and actually establishes a connection. Tells Slurpee, hey, Slurpee, I want a connection through 10.0.0.1 on port 80. Well, the browser bucket retrieves the list of connections required, compares it to the previous list, goes, that one's new. I don't have a connection available for that. I'm going to create one. Now, what I'm doing, it's a little bit sneaky. I don't actually have the bucket handle its own connections. I don't have it open its own flash objects. No. It opens up an iframe to a second location, to a location that is specific just for that IP address. The name is dynamically created. Remember, I own the name server. I am the name server. Now, this bucket opens up this second level iframe, and it's going to have flash objects to service that particular series of requests. And this second level iframe is called a socket. It's like a socket, but it sucks. So, you end up with a bucket of sockets. So, let's see how this actually works. And unfortunately, I don't have wired nets. I'm not going to be able to give you the live demo. But, we do? We'll try. Demo of how this works. When there's an actual connection to 10.0.0.1, and you'll see over there in the top right, the destination port is 80. We have a bunch of state. Is the client connected? Yeah, the browser's connected, or in the connecting state, the server's connected. We have some data to browser. These are base 64 encoded records that describe, please send record 0, please send record 1, please send record 2, please send record 3. Now you'll see that there's sequence and acts. Yes, I admit it. I ported TCP to JavaScript. I had to. But this is basically the nature of the messages that are getting exchanged back and forth. So, I was very amused when I realized that this was actually the title. In order to get the actual connectivity from the browser to the various destinations, You gotta mess with Flash. We can't do it in JavaScript alone. But I didn't really feel like getting the Flash programming environment, and there was this great language called Hax. Okay, the language is called Hax. I have to use it. Hax actually compiles not just to Flash, but to JavaScript, and I had it create an object for me. A Flash object that I could say, hey, Flash, go ahead and make this connection. And then I had to say, okay, what do I have to do to make Flash make a connection to an arbitrary port? How many DNS queries does it take to get to the center of a corporate network? 3. Query 1, we got to load the movie. We load the movie, that does a DNS query. Query 2, we got to load a security policy, whole new thing. Of course, we're still hosting the security policy. 2. 4, we go ahead and do query 3. We got to tell the DNS server, hey, DNS server, you're going somewhere else next time. The next time someone comes to you with a query, where you want to go is actually 10.0.0.1. And it arms. It's ready. It's ready to go. Query 3 happens. We make our connection request to 10.0.0.1, and that goes straight to 10.0.0.1. 3. Now what? We have a connection. We have Flash having a socket to some location. Is that enough? No. Flash needs to actually be able to migrate this data around. So, here is the life cycle of a connection. First, data is received by Flash. There's actually a event that is fired when the socket receives data. Well, Flash is not actually going to be sending the data. Who I want to send the data is actually all the way back up in, not even any of the sockets in JavaScript, in the bucket. I want the bucket to handle communication for all of the children's sockets that are below it. That way I have one nice object that I'm passing back and forth and doing state synchronization on. So, this is what happens when you wave your hand too much. I'm vulnerable to a hand-waving attack, apparently. All right. Can you hear me? Rock on. We're back for more. All right, so check it out. Here's how we're going to do this. I've got a Flash applet. It's receiving data. I don't want the Flash applet sending the data back to the attacker directly or to the proxy directly. I want it to happen all the way back up in the browser. What's one of the other reasons I don't want the Flash applet doing it? If the Flash applet does it, it might send the data back to the socket destination. No. Flash's job is to send the data to the socket. The browser's job is to send the data to the proxy. But don't worry, there's a bridge between Flash and JavaScript. Haxi makes it very nice. It gives us a remoting layer. What we're going to do is we're going to take the data from Flash. We're going to put it into the second level iframe, the socket. The bucket is going to say, oh, I've got to do an update. It's going to go to each of the sockets. It is going to drain each of the sockets of all the bytes on each socket. And is going to pull it all up. Then it's going to send that out. Server's going to receive it. Server's going to acknowledge reception. I'm not going to assume that it arrived correctly. TCP should be reliable, but remember, HTTP, frickin' weird. The proxy is going to receive the update. It is going to send its stuff out on its sockets, on its own sockets, on the attacker sockets. And you know what? The attacker sockets might have some replies, might have some data coming back. So that is going to come into the attacker.